So good morning, class. Our topic for today is about logic gates. So logic gates, what is this logic gates all about? These are the gates or the devices that are used mainly in electronics or electrical, and it's used in microelectronics or digital electronics. But the principle can also be used in the fluid mechanics or fluid system because the principle of the combination of the flow is there. So here we start with the AND logic. So what is this AND logic is about? So AND logic requires two inputs. So requires two inputs. So if I may draw it in the electrical here. So this is input A, input B, this line 1, line 2. What AND logic is all about is that it requires two inputs to become active. So let us define, for example, 1 is the active or on or high logic, and 0 is like off. No, it's not active or low. No? Meaning it requires both the two inputs to become 1 or high so that we will have an output, let us say Q, to have 1 also. If you understand it, it requires two switches. Yeah? I may redraw this. For example, I have two switches here, switch 1 and switch 2. It needs both switches to be inactive, yeah, or to have a contact so that this one will have a light. For example, if I turn on this, the power or electricity can flow here and then energizing the lamp. And then it goes to the line 2, which is basically a closed circuit. And that is the meaning of AND logic. So here the diagram is always in its basic or natural condition. They are normally open, normally. Okay, so we can prove this using the so-called truth table. Yeah, truth table. So how do we design or construct a truth table? Yeah. So we can construct a truth table by using this configuration. It is based to the 2 or the binary number, right? For example, the base 2 to the n. N stands for the number of inputs. So how many inputs do we have here? A and B. So we have two inputs. So if we calculate this, 2 to the second power is 4. So that number 4 is the number of horizontal line. So I'll put 4 horizontal spaces here. 1, 2, 3, 4. Okay? And then I will put the input here. How many inputs do we have? A and B. Okay? A and B is the input. Then we have this Q, the output. You can have any other variable rather than Q. But normally, internationally, and in the textbook, the one that is being used is the Q. Now, so how do we construct a truth table? By the way, the truth table is the table that tells the true status of the circuit. That's why it's called truth table. And the truth table is in this configuration 2, 4, 8, 16. you cannot find a 1, 3, 5, 7. So it's based on binary, because here 2 to the 0, 2 to the 1 is 2. Here is 2 to the 2, or second power. Here is 2 to the cube. Here is 2 to the 4. So here, the exponent, as I've said, these are the inputs. Okay, so for example here, you can have 3 inputs. Yeah, so switch 1, switch 2, switch 3. Switch 1, switch 2, switch 3, and this is the output. Yeah? So here, switch 3, switch 2, and switch 1, they fall under this configuration, 2 to the cube, because there are 3 inputs, and you will have an 8 rows, 1, 2, 3, 4, 5, 6, 7, 8. But we are just here, yeah. So 2 inputs, that's why we have 4, yeah. 1, 2, 3, 4 rows, yeah. So how do we construct the truth table for this n? We might begin with this off, on, off, on here, because we are now in the second exponent. Yeah, here is 0, 0, 1, 1. Yeah. So how do we explain this? For example, we are not doing anything in this switch. Yeah? Both are off. Can we have output? No. So this is 0 or off. Now, I might want to change the status of B. Here, B. If I put a contact here, no, the normally open becomes NC, which is normally closed. Before it was normally open. The current from line 1 cannot pass here because this is open. Yeah, it can not even reach the point E. So if I have here, do I have an output? No, I don't have, because this is open. So this is also 0 or off. So we go back to the initial or normal condition. What if I change the status of A? So A is normally open, then I switch. I switch like this. The current can pass here up to here only, but it cannot pass here because it is open. So look at this, the switch. So this has electricity here flowing. The molecules or the atoms are flowing here, but only up to here. It cannot pass here because it's still open. So if I turn on the A, but the B is 0 or off, still the status is off, right? So now the question is, when is the output will become on? So this output will become on when we have this fourth condition, 1, 1. If we turn on the A and B, if we switch the A and B, it will deliver a current to the lamp like this, here, and it will make a closed circuit. So here, if I turn this on, the contact will become closed. This will become closed. Then the electricity can flow here. Look at this. I may use another color so that it will become more clear. The electricity can flow from line 1 to line 2 without obstruction. So that makes a closed circuit. So here, 1, 1, meaning 1, 1, on, this will make the output on. So this is 1, 1 plus 1. So that is AND logic. It requires 2 inputs to become on so that the output will be having a high value. Again, I'll put this 1, 1, the electricity can flow and it will energize or light up the output. So here, I switch this, it will have a contact. I switch this, it will have a contact. The 0 becomes 1, the 0 becomes 1. Then the logic, the electricity or the signal can pass here, and then energize whatever output we have, and then it will reach the line 2. So it will have a complete circuit, and that is basically the end logic. It requires two inputs to have a high value or active or on, so that the output will also become on. So if you can close, it will become 1. But the original is here. It is normally open, normally open, normally open, and normally open. So when I turn on this and turn on this, it will produce an output or active or high value. So basically that is the AND logic. Thank you.